Hey guys, and welcome to my screencast on populations. This comes out of chapter 5 in our book, and today we'll be talking about how populations grow. First, let's define what a population is. Again, a population is a group of individuals of a single species, and that's the key, is that it's a single species of organisms. So we're talking about all one kind of organism now, and these organisms obviously have to live in a particular place and obviously at the same time. When we look at populations, we can look at a lot of different things, a lot of different aspects about a population. We first look at its size. The size is simply the number of individuals the population contains. That's simply just counting up how many organisms are there, and that's the population size. We'd also look at the density. Density, we have to know the size, but we also have to know the amount of area that the population takes up. And so by dividing the number of individuals per unit area, we'd find the density. This could be like so many organisms per kilometer, per square mile, something along those lines. And then finally, we can look at the population dispersion. This is kind of the pattern of spacing, or how they are spaced apart. Usually when you guys are in class and you're sitting in rows and columns, you're pretty evenly spaced. We'd call that a even distribution. Or at lunchtime, you're sitting around a cafeteria table, you're more clumped. So it's really just how much space is in between the individuals. So looking at patterns of dispersion, we look at the geographic range and we look at the local densities, and we can see that they vary considerably. And they form what we call different patterns of dispersion. And overall, dispersion is pretty much dependent on where the resources are. You know, resources really kind of control where organisms are at. You know, we'll look at a water hole. Most organisms will be around that water hole. Again, take our cafeteria example. Your resource at lunchtime is sitting at the table, eating your food, and talking with your friends. Now, in general, we find three different dispersion patterns. We see clump dispersion. Here we have a school of fish. All these individuals are clumped in patches. Okay, use a little diagram over here. Schools of fish tend to help the fish avoid predators. It's hard to target one single fish. It keeps them safe. I guess you can consider that a resource. Again, our watering hole example would be another example of clumped dispersion. Next, we have random dispersion. We see this a lot with plants because each individual is kind of independently spaced from the others. Plants don't really get to decide where they want to grow. They just happen to land there. If the conditions are good, they grow. And so if you look down here, this forest, all the trees would be a random distribution or random dispersion. And then lastly, we have uniform. These penguins show a uniform dispersion. They're all evenly spaced from one another. Okay, here's a little diagram to show each little dot is evenly spaced from the other. A lot of territorial animals like penguins and lions and so forth show this kind of dispersion because they want to claim their own territory. Now, even though the penguins have their own little nest, they don't want any other penguins coming into that nest because they claim it as theirs. So that would be more of a uniform dispersion pattern. Next, we're going to talk about population dynamics. And in population dynamics, this word dynamic means to change. So we're going to look at how a population changes over time. Okay, how a population essentially, we also say, grows over time. And there are three major factors that go into populations changing in size. We have the birth rate, which is basically adding individuals to the population. We have the death rate, which is basically taking out individuals from the population. Sometimes people refer to this as mortality rate, especially with the human population. This word death kind of has a really dark meaning to it. And so the word mortality rate is often used. They really mean the same thing. And finally, we have life expectancy. And life expectancy doesn't really add or take away. More so, life expectancy is just how much does each generation overlap. You know, the longer the life expectancy, the more often you'll have, grandparents, great-grandparents, and great-great-grandparents all living at the same time because they live longer. So that will affect the population size. So this general equation can be used to describe how a population will change in size. We'll take the number of births and subtract from that the number of deaths, and that will give us our change in population size. So let's take a look at this. If we were to have a positive population size, a positive number for that population change, that would mean the births have to be greater than the deaths. That would give us a positive change in the population. The population would be growing. Now, if we change this and we say we're going to have a negative change in the population, that would mean the births have to be less than the deaths. The deaths outnumber the births, which means the population is decreasing. We could also say the population does not change in size, so that number is equal to 0, and that means the population, or the births, will equal the deaths. So those are all the different ways a population could change in size. Now, what also affects population growth rates is the idea of immigration versus emigration. Just like births are adding individuals to the population, immigrating organisms would add individuals to the population. So we'd have to take that into account when looking at population growth. And just like deaths are taking individuals out of the population, emigration are taking individuals out of that population as well. They're not dying, but they're just moving to a different population. So that would also affect the growth rate. So ecologists have to factor in immigration and emigration when figuring out if a population is growing or if a population is shrinking. Now finally, we have two models that describe how a population grows. The first model is called the exponential model. You may have heard this word in math class. This describes the growth at a steady rate in a population. We're going to assume that the birth rate and death rate are staying the same. They're being held constant. One's not increasing and decreasing over the period of time. They're basically staying the same number. We're also going to assume immigration and emigration are not playing a factor. So under ideal conditions, when we have lots of resources, lots of food, lots of water, lots of places to live, a population is going to grow rapidly, and it's experiencing what we call exponential growth. Okay, exponential growth is said to be happening. This is a very rapid growth in the population. Under ideal conditions, we get maximum growth rate. The population is producing exponential growth. We have a graph of this. If we were to graph exponential growth, it'll look something like this. Let me clear this out. How's the graph? Time here on the x-axis and number of individuals on the y. Exponential growth would take this kind of shape. It's a J shape. The population starts out small but grows very rapidly in a relatively short period of time. That would be our exponential growth graph. Here's another picture of it. So here we have growth of bacteria. In a matter of hours, we go from having 0 bacteria to over 300, or sorry, it looks like 200,000 bacteria. Okay, and that's over a matter of 4 to 5 hours. Elephants are a little bit slower in their reproductive rates, but they would also experience exponential growth as long as resources were unlimited and not affecting their population size. If you guys want, you can watch this little video clip at your own time on exponential growth. The second type of growth rate is logistic. And this is what we typically see in most cases. And this is because resources are usually limited. There's not an unlimited amount of food, unlimited amount of water, unlimited amount of space. They become limited as a population gets bigger. And as a population gets bigger, it gets closer to what's called its carrying capacity. Carrying capacity is basically the maximum population size the environment can support. There's only so much food available, so much space available. Eventually, the population is going to reach a certain size where the resources can't sustain anymore. So at this point, the population stops growing. We get a 0 growth rate when the number of births equal the number of deaths. This graph looks something like this. We graph our x versus y again. We put time on the x-axis and number of individuals on the y. We start out exponential, but then the population starts to slow, and then we level off. This slowing means the birth rate and the death rate are getting closer to each other. They're not equaling 0. The population's still growing, but they're getting closer to the same number. They're getting closer to canceling each other out, and when they do cancel each other out, we get 0 growth. This line here is the carrying capacity. It's the number of individuals that population can, or the environment can hold. Now, usually we don't see a perfectly flat line like this in the real world. Usually the graph will kind of fluctuate around the carrying capacity. It might go really far down, it might go up, it might go down again, and it fluctuates around that carrying capacity. Usually it's not a perfectly straight line like it's pictured here. So here's another picture of this. So here we have number of organisms and we have time. We see phase one, the population is growing rapidly, resources are plentiful for the small amount of organisms there. But then as the number of organisms increase, growth slows because resources become more limited, and eventually it stabilizes at the carrying capacity. Again, if you'd like to watch another video of this, you can click on this link here, and that'll take you to a short clip on logistic growth. So here are our two models. We have exponential growth. We call this the J curve because the population is growing rapidly. Well, the resources are usually unlimited in this case. That doesn't really happen in the real world. And then we have logistic growth where we get exponential at first, but as resources become limited, we reach a carrying capacity and the population levels off. Tomorrow, we'll start talking about limits to this growth. Hope this helped.